Welcome everybody to today's Heidelberg Joint Colloquium. We're very grateful and privileged to have Stephen Smartt from the University of Oxford here to speak. Before he is introduced by Fabian Schneider, I'd just like to remind people, if they could, to sign the attendance form, which is going around. This is sort of useful for us for bureaucratic means of maybe getting refreshments paid for. Thank you very much. So, without further ado, I ask Fabian to introduce Stephen.
Thank you very much, Richard. So it's a great pleasure for me to introduce Stephen Smartt to you. So Stephen did his PhD at Queen's University in Belfast, finished in '96, and then moved over to Cambridge and also joined appointment at Canary Islands. So you've been the Isaac Newton group of telescopes there. Today and thereafter, you went first back to Belfast. You're still a professor now in Belfast, but also the Philip Betten Professor for Astrophysics at Oxford University. And you're now the director of the Hinsey Center for Astrophysical Surveys. And I guess they could not have hired any better person for exactly this particular job. So Stephen's research theme is all about time domain astronomy. He's worked on supernovae, on gravitational wave follow-up events and searches, and he was a key figure in discovering, for example, the very first electromagnetic counterparts to a gravitational wave merger event. And I guess we're going to hear much more about that today. And he has led or co-led tons of collaborations. So if you ever want to know how to lead a collaboration, I think Stephen will probably know what to do and what not to do. There's a gigantic list of awards, prizes, lectureships that you have had, and I don't think I'm going to read all of them, but maybe just a few. So he's a fellow of the Royal Society. That's the equivalent in Germany probably to the Leopoldina. You have been honored with joining the, hopefully not getting this wrong now, the Commander of the Order of the British Empire. So this is the first step to becoming a knight, getting the knighthood. In the UK, I think this is really one of the most prestigious honors that you can receive there. He has had an ESC advanced grant. He has won the Herschel Medal of the Royal Astronomical Society. He is now a Royal Society research professor, and so on and so forth. So I could continue endlessly, but I think it's more interesting to hear about the science. So please, stage is yours.
Thank you, Fabian. So let me talk to you about this topic: compact star mergers, kilonovae, and the R process production, or the production of the R process elements. And the question I want to answer, which I'll come back to, can neutron star mergers form all of the heavy elements heavier than iron? But do we have evidence from the data that we have and the theoretical interpretation of the data that supports that? Or is there another production mechanism that we need for the heavy elements? So I'll put up a few milestones of slides with a few words on them, just to try and guide you through this story. For gravitational wave astrophysics, I'm not involved in those experiments. What I do is actually and have led survey teams that follow up on gravitational wave detections and survey the sky in optical and infrared light, translated like data gravitational wave detections for high energy from stuff. So in terms of gravitational waves, the two big milestones in the field, as you'll know, so there have been 4 observing runs with the LIGO-Virgo gravitational wave detectors and Kagra in Japan, but it's not as sensitive as these 3 detectors. The first run in 2015-16, the second one in 17, the third one, and then the 4th started in June 2023. Initially, it was planned to have it lasting for 20 months. It's still ongoing. They had some breaks during the current 4 run, and that will likely finish around October, November this year. So just to put that in context, the the milestones, the discovery milestones in this field were, of course, nearly 10 years ago. 15th of the 14th of September this year will be 10 years since the discovery of gravitational waves. This very significant event, highly significant signal, was found in their engineering run. Building run LIGO. You can see the waveforms here, the data that they released. On the x-axis here is time versus frequency of the signal. You can see the signal increasing in frequency. Look at the time axis. At the 0.15 seconds, the signal lasts, but it's clearly detected. The button's green. Yeah. Yeah, how's that? Can you hear me? And can you hear me online? Is it good online? Maybe I just need to speak up on here. Is that better? Okay. Okay, I will speak more loudly. So this event in 2015, as you can see, look at the signal here, 0.15 seconds, very clear signal, two black holes, 3629 solar masses, major surprise at the time, I think, given the masses of the black hole. Found very quickly, redshift 0.1, 400 megaparsecs. Now we know that's actually quite a common event. It's about 5 per year at redshift 0.1, 400 megaparsecs. This is sort of the closest, 300 to 400 megaparsecs, about the closest that we have for black hole, binary black hole. But it's common to find these high mass systems. 2017, this was quickly followed by first detection of a binary neutron star merger. You can see the signal here in the time frequency diagram. This actually lasted for about 60 seconds compared to 0.5 seconds. Again, very strong signal here by eye. This was accompanied by a gamma ray burst 1.3 seconds later in the same region of the sky, and 11 hours later, a big counterpart in its galaxy, and I'll talk more about this one here. This one, standard neutron star masses were inferred from the gravitational wave signature, 40 megaparsecs, factor of 10 closer than the binary black hole merger. And needed anything else? Oh, you want me to use it? Okay. I'll take it.
Okay, so now the difference here, 40 megaparsecs. This one was found at a factor of 10 in difference in distance. We all get very only the second observing run. Turns out we got pretty low. This is probably, and I'll show some evidence. This is probably once in a decade event. Probably, we don't know for sure, but we haven't had one since, or else it'd be probably my second slide would be the second one. We haven't had one since. We haven't had an electromagnetic counterpart of a gravitational wave source since, I would say. Although there's one suggestion of one for a binary black hole, but certainly not for a neutron star merger. But I mean, so at the time in 2017, we still think, there's great science return from multi-measure astronomy if we find optical and infrared and high energy counterparts of gravitational wave sources. It will address many of these topics, some of which I'll discuss. Origin of the R process elements, is all of the R process elements, or are they all formed in mergers? The maximum mass of neutron stars, neutron star equation of state, minimum mass of black holes, is there a mass gap? Lots of these questions we want to answer from our traditional way of doing astrophysics and combining observational data with theory. What's the nature of heavy neutron stars or light black holes? There are some objects now from LIGO-Virgo which are in the gap between neutron stars and black holes. If you have a counterpart, you can get a host galaxy, you can get redshift, you can measure the Hubble constant with these. What fraction of gamma ray bursts are from mergers? And something I'll discuss later, do mergers produce long gamma ray bursts? Stellar and binary evolution test the endpoints in the supernova mechanism. there are now groups that have suggested we might find lensed gravitational wave events. I'd like to find some more, first of all, before counterparts, before the lensed versions, but possible. And then, of course, fundamental physics from the comparison of the speed of gravitational waves. So, there is rich science to be done here, but since 2017, we haven't had another example. So we do need gravitational waves and their electromagnetic counterparts and intense follow-up to exploit all of this quite interesting science. So what are we doing in terms of optical surveys of the sky? Before I come on to the what has been done in the area of combining gravitational waves and optical and infrared data. Well, now we can, with a number of surveys across the world, a few of which I'm involved in, the Zwicky Transient Facility, the Atlas suite of 0.5 meter telescopes, the Pan-STARRS telescopes in Hawaii. There are currently 7 0.5 meter to 1.8 meter wide field survey telescopes, and there are a few more started. There's a UK project called GoTo, and a Dutch project called Black Gem in Chile. And with all of these combined, we pretty much survey the whole visible sky every 24 hours with these facilities. Atlas can do, if the weather is good in all 4 stations in Atlas, we can get around the whole visible sky every 24 hours. Plus supplementing it with these other facilities, we pretty much comfortably do that, often multiple times within 24 hours. And that's resulted in a huge number of extragalactic optical transients, which have been found and registered on the IAU transient name server, over 150,000 now since 2016. You can pick out some trends here. ZTF dominating in the north, Pan-STARRS dominating the ecliptic, Gaia producing a lot of transients and which are actually in the plane and likely galactic sources. And in the south, it's pretty much Atlas that covers the southern hemisphere below -30. So huge numbers of optical transients, which are extragalactic optical transients, which have been publicly registered. So from this, there are both ZTF and Atlas. I'm going to show you 2 figures from ZTF and Atlas that summarize the transient population as we see them. Type 1a supernovae, of course, are reasonably well understood in terms of the light curves. Progenitor systems are still debated, but the light curves for type 1a supernovae have a width and a luminosity, and those are correlated, and they can be calibrated given a certain stretch factor or width of the type 1a light curve. These can be calibrated to their common absolute magnitude and used for cosmology, of course. But they've all got a common characteristic of time scale, which is of order 20 days or so. Time scale is the time above maximum light. So their peak magnitude and time scale are reasonably uniform. The peak magnitude is determined by the powering mechanism, which is, in this case, it's radioactive nickel-56, and the width is determined mostly by the ejecta mass, opacity and the ejecta mass, the time it takes for photons to diffuse out, for the radioactive material to thermalize, to products to thermalize and then diffuse out. So this x-axis is driven by mass, ejecta mass, and the y-axis here is determined by the amount of powering mechanism. So if you put all of these on a diagram and plot rest frame duration, time of maximum light, so the width of the light curve versus peak absolute magnitude here, most supernovae live in this clump, well characterized. This clump, most type 1a supernovae are here. The red dots are type 2 supernovae, large hydrogen envelopes. Recombination of the hydrogen powers these supernovae for longer, so they can have durations up to about 100 days or so. So most of the normal population is in this region here. And then there are extremes of this population. There are these objects, which are in this region we call superluminous supernovae. You can see there are not many in this diagram. This is the ZTF Bright Transient Survey. They certainly do exist. They're probably not powered by nickel-56. They've got to have another mechanism, likely a rotating neutron star in the expanding remnant. There are objects sitting below the supernova limit, the supernova locus, but above the nova brightness, these so-called gap transients. There are very fast transients, which are luminous but decay very rapidly. These also cannot be driven by -56. They're just too luminous and too fast. And then there's the regime here, in which there are very few known. This is the region where we would expect, and I'll show you that the one electromagnetic counterpart, 1 kilonova, we know lies in this region. So we have not detected merging neutron stars in optical from anything else yet. So that's this comes from ZTF, and this is everything above a certain price, 17.5, I think is the magnitude. Now, what we've been doing in Atlas is a similar thing, but we put a distance limit on this and say, what is the total, what is the every transient, what's the population of transient within a certain distance limit? We set that to 100 megaparsecs because we're reasonably confident we can find nearly everything within 100 megaparsecs, quite everything, because the faint type 2s will not be detectable right up to 100 megaparsecs. We'll still have different volumes of sensitivity, but the galaxy population within 100 megaparsecs is quite well quantified now. There are not many host galaxies without a red, probably 90% complete in terms of galaxies down to a reasonable luminosity limit within 100 megaparsecs. So we've done a 6-year survey. We think a highly complete galaxy catalogs. We've been using careful host matching between transients and host galaxies. And then we produced 1,700 transients. And this, we would say, we hope to release this in the summer. This is a census of transient objects within that volume of megaparsecs. Again, the type 1As are here, the type 2s are over here, and then we can see these other populations, the gap transients, type X here. These luminous objects, these are all no superluminous supernovae in the local universe. The brightest one is a type 2N, with supernova, which is a certain stellar material. 22 ESA is a type 1A, so not like this, but certain stellar material. We discovered this object, 18 Chi, which I think the explanation for these bright, fast things is likely the type disruption events around intermediate mass black holes. The data are suggesting that's the most likely. And I've put this object on. It wasn't discovered by Atlas, to give you context, because this area is, and this one is the counterpart from GW1717. Fast and quite hard to detect independently in optical red surveys, but this is where. So we've known since the Hulse-Taylor binary was discovered that certainly gravitational waves do exist in nature. Hulse-Taylor binary is a pulsar, 1.4 solar masses, a companion, certainly neutron star companion, 1.39, and the shift in periastron of this system is seen to shift, and the general relativity prediction for this system emitting gravitational waves falls perfectly on time data. So since then, we've known that gravitational waves almost certainly exist. 170817 was a binary neutron star with 1.3 and 1.5 solar mass neutron stars, very similar to the Hulse-Taylor binary. So when this was discovered in 2017, there was a coincident short week gamma ray burst. NASA's Fermi satellite and Integral detected a GRB 1.3 seconds later. This is the frequency time diagram, very convincing that there's a signal here. Detected in both LIGOs, not detected in Virgo, but the non-detection helped constrain the sky localization. And the sky localization was remarkably small. It ended up 28 degrees on the sky, 28 square degrees on the sky. This is where the LIGO detectors constrained it to this area in the sky. In the southern hemisphere, it was actually quite close to sunset. So it was an area of the sky that was disappearing. We can only observe this from the ground for about 2 weeks. Disappeared. unfortunately behind the sun. But within that 60 megaparsec, so the estimate of the distance was about 40 plus or minus 10 to 20 megaparsecs, the estimated distance to the source. So what people did in the first night when darkness fell in Chile was to look at every galaxy within about 60 megaparsecs within that 28 square degrees. The optical counterpart was bright and easily detected, and it was consistent with the location of the calibrators. So this pretty much sums up what was found in the optical and infrared. It was a faint starting blue source in this galaxy, NGC 4993, faded to a red source quite quickly. This is the total luminosity, so 10 to the 42 ergs per second versus the time scale of the transient. It declined very rapidly, so you can see a factor of 100 over 10 days. So again, it's a faint transient source, declined very rapidly. Hard to find those in optical surveys alone. Although this would have been detected both in ZTF and the Atlas survey without any pointing to this region of the sky without the gravitation. So it would have comfortably detected that 17.5. It is detected, but we have not seen a source like that since or before. Can be explained. So the lines on this are models of quite a number of papers at the time and since that have estimated the total ejecta mass of this produced by this source. So what we call a kilonova is the thermal emission from the ejecta from merging neutron stars. Typically only 8% of the total mass of the two merging neutron stars is heated and ejected. And that material, which is radioactively heated and thermally cools and radiates from the optical through the infrared, is what we call a kilonova. The ejecta mass is roughly about 0.02 to 0.03 solar masses. The ejecta velocity is 0.1 to 0.2 c, which has been confirmed in the spectra. Depending on the opacity you use, the mass ejecta mass is dependent upon the opacity and the ejecta mass, determining the time scale of decline. Beta is a parameter for a fairly simple parameter we put into the models to explain the powering mechanism, the radioactive power. The elements inferred in the spectra I'll come back to. But what we have done and what others have done, and there have been more sophisticated models that have done since, but the first order, if you've got many radioactive isotopes, and they are all providing input power, which are exponentials, the sum of those exponentials, if there are many of them, can be approximated by a power. And that minus beta, just that one number, encapsulates all of the complex radioactivity that goes on. And it's actually a really reasonably good fit to produces a reasonably good fit to the observational data. And a number of people use this parameter mechanism for radioactive power. That's a reasonable job. The other thing, so the two things that stand out for this optical source, which I'll come back to discuss how we find more of these, is that you've got a faint source, declines rapidly, and then there's a very rapid blue to red transition in the spectrum. So this is a series of spectra. They're interpolated spectra. Here you'll see that the days go up here by a fraction of a day, but the spectra are actually taken every interchange for 10 days at the BLT. So that was the first spectrum after 1.5 days, very blue. You can see that this was the evolution of the spectra. And as I say, the observational data are taken every day, so 1.5 days, 2.5, right up to 10.5, and this shows an interpolation between them, but it demonstrates that the output, the optical infrared output of this source changed quickly from the optical below a micron to well above. Quite unprecedented other transients that we have seen. And then we ended up with a source that was emitting mostly beyond 1 micron. most of the luminosity was coming out in the infrared, below between 0.5. So what do we think is happening here? Well, the heavy elements in the heavy radioactive elements are produced in this emerging neutron star. They decay with a very short lifetime. They diffuse out, and with that beta parameter of set to about 1.3, we can explain the powering mechanism. So everything highlighted in red is, we think, produced in standard stellar evolution explosions of supernovae and intermediate mass stars, or mass loss from intermediate mass stars. And the question is, how much of this, of the rest of the periodic table, can be produced in emerging neutron stars? So it would be quite amazing to make the statement that they all are, and that's probably not true. Some of them are produced by the S process, in which neutron capture proceeds slowly between decays. But most of these are produced in the R process, where you have to have rapid neutron capture before the decays happen. But how much of these are produced, how many of these are really produced in neutron star mergers rather than anything else, still an open question. I'll come back to. This is the abundance diagram, the standard solar system abundance diagram, where again this dates back to the 50s even, where the standard nucleosynthesis calculations in massive stars, type 1a supernovae, more or less explaining all of the abundance peaks that we see in the up until the iron peak. What we call the first peak, second peak, and third peak in the in the neutron capture R process are labeled here. First peak around strontium, second peak around xenon, barium, and the third peak is around platinum and gold, with this bump in the middle for lanthanides. So what are those? Did the kilonova produce any of these, or what fraction of each of these peaks could it have produced? Well, even before the detection of 17-17, there were a number of groups that had done quite sophisticated calculations of neutron star mergers, and then calculated the nucleosynthetic products from the mergers from simulations. Here's this is an example from Stefan Roswald, and these are 3 examples of taking a hydrodynamic simulation of merging neutron stars and calculating the nucleosynthetic products with different electron fractions. Okay, so different ratios of neutrons to protons in this in the ejecta. And you can see, so for high proton fractions or high electron fractions, you typically get the ejecta is dominated by light R process elements, what I would call the first peak, and peak in this diagram. So if you've got relatively low neutron fraction, you tend to get these elements produced. If the material is relatively rich in neutrons, the ejecta is dominated by the heavy elements, platinum, osmium, gold, for example. In the middle here is an intermediate electron fraction material, and that's got a mixture of the first, second, and third peaks, and some lanthanides. So the lanthanide fraction is given here. Remember, the lanthanides are these elements down here. Because they've got complex valence electrons, these can produce very high opacity in the material. So even a trace amount of these can really affect the color of the event that we see, because more of the optical UV light is trapped. So these have a very large effect on the color and the spectra of the transit. So this one in the middle has got 5% of the lanthanides. This heavy third peak composition's got 30%, and this first peak is hard to get in. So Andy Boisfine, Stefan Gorley produced 12 different trajectories from iron-rich to platinum gold-rich material. And we used those and put it into radiative transfer models. So this was done by Stuart Sim, myself, and a PhD student called James Gallanders, who's not a postdoc in Oxford. The radiative transfer model. So, you know, these tell you what we think is going on. You've got to convert that to an observational signature. The way we do that is to run a radiative transfer model that takes the compositions from these simulations and calculates how the radioactive decay particles will power the ejecta, and how we will see that in terms of the spectra and the colors of the transient event. So this TARDIS radiative transfer code is relatively simple. There is more sophisticated codes available. The advantage of this is that it's fast and we can do many models, and it's a starting point. It's certainly not the end point of these events, but it's something you can use quickly to get an idea to be in the line forming region. And it's been used successfully for supernovae for many years. The difficulty, of course, with supernovae compared to stellar spectra is that the ejecta are very fast. It can be difficult to identify individual elements, but it has been used through that in the past. There have been other multicolored methods by other people in the literature applied successfully to supernovae. So we attempted to do this and have been revising this over the last few years. The results of this, the bottom line is that between 2 to 4 days after merger, you really do require these heavy elements in the spectrum. And the reason for that is that this is the black line is the X-shooter spectrum. Look at the red line is what you would expect. So we started with this first peak, the element production mixture from synthesis calculations. We started from the lightest elements that could possibly be formed, and they produced the red line. And the only way there's a very large suppression of flux. The only way we could reduce that by adding more elements to increase the opacity in the blue and reduce the emission in the blue. And so the best composition we could find was mostly one of these intermediate blends, which had 5% lanthanides and quite a lot of the intermediate the first and second peak elements. So if you look here, this gives you an idea of which lines are producing are making the features, these observable features. So the main one at 1 micron is strontium, and in the blue is being affected by lanthanum and cerium. Those are the dominant lanthanides, reducing the opacity. So there isn't really, we struggle to find any other way around this. The observed fact that it starts off very blue, becomes red, and it's a combination of more of the light coming out in the infrared and flux blue, and quantitatively do that is with some. I think most people would probably accept that's true. How much is still to be determined. Still, this is a 1D LTE calculation, but I think that is probably true that you do need to suppress the flux in. Now, what happens after 7 days? So we observed this for about 10 up to 10.5 days after the merger. As the spectra were taken, they went from what seemed to be, these look like they're optically thick spectra, broad absorption lines. That line is almost certainly due to strontium, and it's a P Cygni line. So these look like they are optically thick photospheric spectra. But after 7 to 10 days, they transformed into what we would call optically thin spectra with a continuum and then emission lines on top. And the fact there's no absorption associated with these emission peaks suggests that these are collisionally excited transitions that are then emitting. The photons are coming. We see them because the material. So all those features that we identify as the spectra progress have all got similar. Doesn't mean they're all individual transition velocity, but given that there's still very high velocities here, it's not easy to say that these are individual transitions that are dominating the emission line features. But we started out with that. And James, as part of his PhD thesis, he went through the whole of the NIST database. And he looked at low-lying transitions, which might be relatively strong, that had plausible transitions that coincided with the central peaks of all of these features. So in his paper, he these candidate strong ions, and then he also found multiple features, particularly for tellurium-3, and there is a tellurium-3 line exactly at 2.1 microns. Kenta Hoda-Gazaka also suggested that this line at 2.1 microns is due to tellurium. This is an optically thin, collisionally excited one. And that the total mass ejected is 0.05 and about 3 is due to tellurium-3. That's probably the most likely identification of this, and I'll come back to that identification. But what has happened since 2017? So this was an interesting result that we found that could explain most of the spectra with the blend of the R process elements. That there's a reasonable estimate and reasonable consensus about 0.03 solar mass in total was ejected. What has happened since 2017? Well, LIGO-Virgo went through a third observing run. So this happened back here, 2017. LIGO-Virgo-Kagra went through their third observing run, and we're now well into the fourth observing run. Still no detection of another electromagnetic counterpart. In 2003, there was one further event, which was a binary neutron star merger event in April 2019. So this is quite an impressive detection. There's a little movie here that will loop, and it will blink back and forward, the detection, non-detection. You can see it. So you can see the signal here. If I trace that down, you can see it blink back and forward, even down here. There's a signal. So impressively, they found this 2 minutes automated search with one detector. There's only one detector that detected this one. Of course, they do know what they're looking for. It's not like they're finding just a random signal in the noise. They know what the frequency time curve would be, so it's much, which gives them the confidence to find something quickly in these noisy data. Unfortunately, there was only one detector on at the time. And this one was 150 megaparsecs, not 40 megaparsecs. So the signal's weaker, of course, but still there. Still visible, but they were able to get an alert out within 2 minutes automated. The distance to this was about 150, 160 megaparsecs. The estimated total mass of the source was actually quite high for a comparison to the galactic neutron star sample. By 3.2 solar masses in total. GW17 and WAIT17 sits here. These are the galactic neutron star binaries. So this one was on the high side. There was no optical so we searched a number of high energy satellites, searched the region. ZTF searched the northern region of the sky. Unfortunately, because it was only one detector, the sky area, instead of being 28 degrees, was 7,460. A bit more of a challenge to find a counterpart within that large region of sky. And unfortunately, that region here was bound. So although there was no counterpart detected, I'm not even sure that it's any sense because half of it could have been a very bright counterpart, but we could not observe that region of the sky. So nothing else was possible from that So what about short gamma ray bursts? Do they signpost kilonovae? So we've had another binary neutron star merger since 1717, no counterpart. But given that it's a short gamma ray burst from 1708-17, although albeit a weak one, and for many years people have assumed that short gamma ray bursts are produced by merging compact objects rather than collapsars and supernovae. Can they signpost kilonovae? So I wrote this back in 2017, this slide, and I thought probably not. Which is for kilonovae because of this slide, because they're basically not first. So this is a histogram of the redshifts of short GRBs, and the short GRBs are here, and really just you don't find them within 400 megaparsecs, redshift 0.1. At that stage, virtually all, I think all short GRBs had been found beyond 400 megaparsecs. So the chances of finding distance limit, the distance range for LIGO-Virgo, 160 megaparsecs. So how could you possibly get a GW source and a gamma ray burst? Because we just don't typically, and it's not like you can point the satellites deeper. That you can do. You can do that in the optical. We can't really do that at high energies. So the chances of finding a GRB and a gravitational wave was expected to be pretty low. So I thought unlikely you were going to get high energy, help with localization. So probably the best look in optical surveys, or perhaps UV and radio surveys might also be possible. But I thought, well, short gamma ray bursts. Turns out I was completely wrong. So I think this is the biggest surprise since GW 1708-17. Since then, although we've had from gravitational wave sources, no detection in the optical or infrared, there have been 2 detections of a kilonova signature, but in long GRBs, not short, 2 long GRBs, standard, which look like standard long GRBs. In fact, this one, 230307A, second brightest GRB of all time. It was a fairly standard long GRB, although X-ray feed. At a distance, relatively close distance. Well, I'll come back to the distance. It turns out it is at 280 megaparsecs. But at the time, this afterglow was found. So there was a GRB, bright GRB. The afterglow was located. This is a JWST image of the afterglow once it was found from the ground. So the afterglow was located, declining fairly rapidly, and this galaxy was spotted quite a long distance away. So if this is at the same distance as this, that's 50 kiloparsecs in terms of the offset. So at the time, I was also wrong. I thought those are probably not related. And the reason, so I was involved in follow-up of this and thinking and wondering what is, so at the time we didn't know this was a kilonova and likely be a merger. We just thought it's a fairly long GRB. It's possibly associated with this. It's possibly a high redshift galaxy. We got some James Webb Space Telescope data at the time, which I'll show you this first before I show you the results. So at the time we got JWST data, and so that was the afterglow. The little yellow dot, there seems to be a galaxy here, and so there was, when we were looking at this, there were 2 camps. Some people thought this is associated with that, or others thought, well, it's actually associated with that. Turns out that galaxy is at a redshift of 4.79, and you can see H alpha, oxygen 3, and H beta here. So clearly, and it's in the slit. That galaxy just overlaps the slit. And then you've got this diffraction star here as well. So it was quite confusing at the time. I thought that's not associated with that. It's probably a high redshift GRB. It's long GRB. It's probably high redshift. Find these all the time. Now, if it had been a high redshift, it would have been easily the most luminous GRB of all time, given it was the second brightest. So at redshift 4.79, it's off the scale. It's a different explosion. I remember someone fitted this. We got a spectrum from James Webb, and it was also ambiguous. And someone immediately fitted this spectrum and said, "Oh, I can fit that with a redshift 0.79 galaxy with prospector," which makes me suspect prospector results if any of you use that. But there was this feature at 2.1 microns. We did take out. So the only thing we thought was, we have this afterglow. We better take another spectrum on another image to see what happens. So turns out it disappeared. We got another spectrum, and that spectrum disappeared. The flux fell as well, of course, because this didn't quite disappear. It faded rapidly, but this feature still remained. So then I thought, I think I was one of the first ones to show this on our discussion. I said, well, that 2 micron feature actually is very similar to the 2 micron feature, 2.1 micron feature in GW17 and they are not quite at the same wavelength, but close. So the orange line is 170817, and the other 2 lines are from this new GRB at 280 megaparsecs. So if we believe these really are the same feature, that does effectively give us a redshift, which is pretty close to that. So we do think this actually is a kilonova, or the light curve matched kilonovae as well. So the JWST infrared data matched 170817, which I call 17 GFO here, at this redshift of 0.065. And there are 2 papers in Nature show that the declining JWST data was a reasonably there was a second one. This is more convincing. There was another one before that with no spectra. The year before, there was another GRB at 211211A, again at a similar redshift around 300 megaparsecs, which also had an infrared excess, which looks like a kilonova. So 2 discoveries since 2021, spectacular James Webb telescope data for both of these. So the question is that really tellurium-3? Is it the same thing in both of those? Is it really tellurium-3? And is it the same 170817 and this new associated? So again, James went through the whole of NIST. He looked for any sources exactly at any lines, plausible lines, which are around 2 microns. This line of tellurium-3 has been detected astrophysically. It's been detected in 2 planetary nebulae at 2 of these bright planetary nebulae have this detection. Tellurium is reasonable as a an element that might be produced. It's one of the most predicted to be one of the most abundant elements that's produced in neutron star mergers. And so this is calculation of the R process elements that are produced in mergers. But it's not quite on the center of this feature. So the tellurium line here is in blue. This feature looks like it is had 2 components. It's a blue component and a red component. They can be fit with very similar full width half maximum. In fact, the blue component needs to be slightly narrower, 0.06 C rather than 0.1 C. But these 2 components, which then turn into this 1 component after 60 days. So the first spectrum was taken plus 29 days. The second spectrum with JWST was plus 61 days. The line is still there, but it's shifted to blue. Shifted to red. It's more consistent with the red component, but the tellurium line is right in between the 2. The offset from the rest frame tellurium line is 11,000 per second, about 0.36 of the full width half maximum. So it's not quite at the right wavelength, but so James went through the whole of NIST again, and he found this was really the most likely candidate. There are a few others, erbium, platinum, but they're not quite at the right wavelength as well. So James went through all of the level information from NIST, all the neutrals, triply ionized ions, applied transition rules, look for the parity, LS coupling rules, etc. So erbium, tungsten, and platinum are plausible, but I think the most likely, even though the so where do we go from here? Well, what's the reason for no neutron star mergers from LIGO-Virgo since 2019? And it's one detection, two detections of kilonova from GRBs. And it's probably just the rates, true rates of binary neutron stars in the universe are lower than we expected. This gives you the total number, the figure of merit for the detectors is really the volume that they sample multiplied by the time that they're up, multiplied by gives you the total number of mergers. And if you look at the ratio of this volume times time between 04 and the whole of 01 plus 02 plus 03, it's a factor. So given that we had 2 neutron star mergers in 01, 02, 03, I expect 4, should have thought 4. Integer numbers here. I'll just run with these integer numbers. So it's probably telling us that maybe we were fortunate in the numbers that we found during the 2 that we found during 02. That's what that is. The estimate of rates was quite uncertain, obviously, from just 2 sources. But I think this is telling us that, unfortunately, the rates of mergers are probably lower than we expected from the first 2 ones. I think this, so the rate of binary neutron stars, it was estimated by the LVK collaborations 170. This would mean we've got less than 1 binary neutron star per year within 100 megaparsecs. Remember, that 100 megaparsecs is where we're reasonably confident we're going to detect faint transients. We haven't found any, but we'd expect less than 1 per year. In terms of chemical evolution and the production of the R process elements given this rate, there's been a few papers, and this is one of the ones that looked at this in more detail. By using binary population synthesis models calibrated to the local rates, the R production process would go to any of the binary populations. And these are already calibrated to this is which suggests to me that there's another production mechanism for the R process, not just binary neutron stars. So the conclusions, well, multi-measure astronomy is still very exciting, requires GW and a electromagnetic counterpart. Total number of kilonova discoveries enabled with gravitational waves. I may not go up very much in the final few months of 04. Kilonova discovery just with wide field surveys, 0, which may be changed by Rubin and the LSST. But kilonova discovered with nearby GRBs already 2. I don't even know what we're looking for. This may be the most productive way. I think the discoveries are likely limited now by the natural rate by neutron stars, not the instrumentation within these projects, but they are lower than we had hoped. And also, likely not all LIGO-Virgo-Kagra neutron star mergers will have kilonova detected. Any help being true. Can binary neutron star mergers supply all of the R process elements? I think that the answer to that is I think we don't know, because the true rates of binary neutron star mergers probably present. The mass ejected per binary neutron star merger probably a factor of 2. The ions and the elements, I've showed you 2 reliable identifications, strontium and tellurium, not sure of the others. And another major uncertainty is the atomic data for these heavy elements is definitely incomplete. We need calibrated transitions, oscillator strengths, relational data. And there's a lot of work in Europe ongoing, particularly Germany, Denmark, and UK. There's a big ERC synergy grant to try and put all of this together. But given this uncertainty, I would say we really don't know if process elements. I think the 05 time when the gravitational wave detectors reach their optimal sensitivity, combined with the Rubin Observatory, is probably the only chance we have of increasing these numbers beyond. But that's not until 2027. Thank you.
Okay. Okay. Can you hear me with the mic? Okay. Thank you very much, Stephen. This is a fast start and a little bit of a stumble, but it looks like it's going to build up again quickly in the future. I would like to open the floor for questions from students initially, if possible, if there are any who would like to start the ball rolling. Yes.
So thank you for your talk. You talked because of close supernova transients, so like redshift 0.1. With James Webb, we discovered many new high redshift supernova, and there are many new PRM in the next cycles where we want to observe more transients. What do you hope or expect to get from this new data?
So James Webb can, it's got a very narrow field of view. So if you're doing a survey with James Webb to find things, you're typically going to find them at high redshift, quite high redshift, because that's where the volume is and the sensitivity of James Webb. So the other way to use it is if you find something from the ground and then follow it up quickly. In terms of the surveys, I think, can that tell us any more about the supernova population? I think the rates of supernovae at high redshift is an interesting thing that will come from James Webb. Do the supernova that we find at redshift 3, 4, 5, perhaps, do they look significantly different to the low redshift population? We'll never be able to study them in as great detail as we do for the low redshift population. But any sign that the supernova population is evolving as a function of redshift, because it can get so high redshift compared to what even Hubble Space Telescope surveys, I think that's the most interesting thing. Do the progenitors look different? Do we find unusually massive stars at low metallicity, for example, in the high redshift universe that produce very different supernova that we see locally? That's what I would be looking at.
We had one open the questions to the floor to everybody. One here, form.
Nice talk. The kilonova from the long GRB, is it still expected to be a neutron star merger, or is it expected to be something like collapse? Or we don't know. Yeah.
So we don't know. Obviously, without a gravitational wave signature, we don't really know that that's a merger. All we know is that as the afterglow faded, there's another component, and that component is best matched by what we saw from 1708-17 and theoretical models that come from neutron star mergers. Could it be another type of it points to the R process, and the inference that it's a neutron star merger is just an inference. I think what the data would support is that there's high opacity material and there's a line that might be tellurium-3. That's what the data would suggest. It's an infrared bright component that is explained by our process with the opacity you require, and then what produces those. So there isn't independent evidence that that's a merger. It could be yes. It might not be a merger, but it's another R process site. But it doesn't look anything like, so that at that redshift, if it had been a collapse or in a supernova like thing, we would have seen a completely different optical signature. So it's got to be a very low mass ejecta and high opacity material.
Hi, thank you for the comprehensive overview. I have actually two questions. One is about the black hole neutron star system, because in O4 we have some candidates, and one of them was also published as a special event by the LIGO-Virgo collaboration and no electromagnetic counterpart. So what do we learn from it? And the second question is if you can elaborate a bit on the way you estimated the rate, the merger rate density of the associated with the two long gamma ray bursts that look like kilonova.
So on the first one on, so yes, there've been a number of neutron star black hole mergers. They're at mostly larger distances, and the sky areas were mostly not very small, not particularly small. So I think there have been a number of searches. Obviously, no one has found anything. I think the inference there is not that limiting. You know, you could easily have the 1708-17 type of merger and type of optical counterpart, which is not detected for those events. They're just a little bit too far, and or the sky areas were quite large, so they're just more difficult. Those have been more difficult to follow. The rate estimate here of 0.01, but well, I think that just comes from the number of GRBs that we find in the local universe. Roughly. Yes.
Okay, I think we've got time for one more question. In the middle here.
So what do we make of this 50 kiloparsec offset for this event? That the amount of kick that you need to get there if it's a neutron star possible.
Yeah, good question. So it is possible to do that. It is possible to do that. There is an estimate of the ejecta velocity that you need, and of course this could be 2 gig years, 3 gig years in terms of the delay time between formation and when it forms. And 50 kiloparsecs is about. We do see transients in the local universe, unusual transients, typically the gap transients and then other unusual thermonuclear explosions that are out to 30 to 50 kiloparsecs from their hosts. So that's why we thought that is plausible. We don't see many that are beyond about 50 kiloparsecs. That's about the limit. Then you run into confusion limit with other background galaxies. But the delay time, that's feasible, roughly works. And we do see transients out to that distance. So that's why we think it might be plausible.
Okay, then I think before there'll be time for more questions over dinner tonight, which will be at the Dorschenker, I believe, from 7:15. If anybody wants to join, please announce themselves to Fabian Schneider. And before then, there's an opportunity for students and young postdocs, is that right? Or yeah. So that's Cormac Larkin is organizing that, so please just announce yourselves to him at the front here if you want to join for drinks. And with that, I think that draws today's colloquium to a close. We thank you very much for this really interesting update on this fascinating field. Thank you very much.